Bumbo. You need to use more force to get your cap back.
You used the word force. But do you know what the word force really means?
Well,
the word force is used in a variety of situations in common parlance. However, in science, force is what acts on a body to make it move or stop it from moving. In this lesson, you will learn about force, its effects, and its characteristics. At the end of this lesson, you will be able to define force, illustrate the effects of force, list the characteristics of force, distinguish between balanced and unbalanced forces, and explain friction. To explain the concept of force, let's first observe some real-life situations. What do you think these people are trying to do?
they're trying to perform some tasks requiring force.
That's right. As you can see, the first task involves force in kicking a ball and setting it in motion. The second requires force to roll a boulder off the cliff. In the third, force is being applied to try and stop a moving bus. Thus, if we use these examples to define force, force is an agent that tries successfully or unsuccessfully to move a body which is at rest or to stop a moving body. Let's go back to Bumbo and Jumbo and their clown act in the circus. Bumbo applies force on Jumbo, trying to push him away so that he can retrieve his cap. Initially, Bumbo does not succeed, even though he's trying hard and exerting force.
I guess he needs to push harder.
That's right. When Bumbo increases the force exerted on Jumbo, he is able to push Jumbo away.
There you go. He got his cap.
This child is applying force, trying to stop the dog from breaking free of the leash. If you have ever taken a dog for a walk, you have probably had a similar experience. A dog that is eager to get away can apply a considerable amount of force on the leash. You can say that a force is being exerted on the bodies in both these cases.
Oh. So here two forces are combined. Looks like force affects our life in a lot of ways.
True, although you can't see, taste or touch force. We all feel the effects of force. A force acting on a body can change its state of rest or of motion, its direction of motion, or its shape. Let's look at each aspect of change induced by force, one by one. In our initial example, the force applied by Bumbo made Jumbo move. Similarly, a push to a stationary shopping cart sets it in motion. A child uses force to pull a box of toys on the floor. A football goalkeeper applies force on a fast-rolling ball to stop it and save a goal. In all these cases, the state of rest or of motion of an object is changed. On a hockey field, when the ball is passed from one player to another towards the goal, players use their hockey sticks to guide the ball. Do you notice that as the ball is guided with a hockey stick, it often changes its direction of motion? This change in direction is also a result of the force applied on the ball through the stick.
And how does force affect the shape of an object?
You may have noticed how a balloon man creates figures from balloons.
Yes. They do that by squeezing the balloons in different places on the balloon.
Right. By squeezing, they are applying force on the balloon. This makes the balloon expand in other areas. You can also observe this effect in a rubber band, a kitchen sponge, or a beanbag chair. A rubber band expands on pulling, while a sponge contracts on squeezing. Beanbags are popular because they take different shapes depending on the position of the person sitting on them.
So how do we identify force?
You identify force using its 4 characteristics: magnitude, line of action, nature, and point of application. Magnitude is the measure or quantity of a force. Magnitude of force is quantified in Newton in the SI system and in dyne in the CGS system. Look at Bumbo trying to push the 2 wooden blocks of different sizes towards the wall. He had no problems pushing the smaller block, but he seems to be struggling with the larger block. There, he's done it. What do you think was the difference in these 2 cases?
He had to apply more force to move the second block.
Correct. The magnitude of the force required to move each of the 2 blocks was different. The magnitude of force is indicated by the numerical value depicting the quantity of force applied and the unit of the force. Line of action is a line along which the force acts. Consider a book kept on a table. Do you think it exerts any force on the surface of the table? Doesn't look like it, does it? In fact, its weight acts as a force downwards on the table. You can say that the line of action of force is downwards. However, if you try to push the book, you need to apply force horizontally. Therefore, the line of action of the force applied on the book will be horizontal.
So, the line of action can be horizontal or vertical.
Not just horizontal or vertical. Line of action can also be inclined. For example, when a golfer hits a ball, he applies force at an angle from a horizontal surface. Hence, the line of action in this case is inclined. A force can be a push or pull force by nature. For example, a cue pushes the billiard balls forward, while a truck pulls a trailer behind it. Finally, let's look at the point of application of a force. The effect of force on a body depends on the point at which the force is applied. To understand what this means, consider the scenario where a clown in a circus is pushing another clown. When the clown is given a push on his upper body,
Oops! He fell face down.
Now, what if the point of applying the push is changed? A push on the middle of his body, for instance. Did you notice the clown didn't fall at all? He simply moved ahead. Now let's see what happens when the push is directed towards his lower body. The clown loses balance again, and this time he falls on his back. So, based on the characteristics of force, can you determine whether it is a scalar or a vector quantity?
Let's see. A force requires a magnitude as well as a direction, right? This makes force a vector.
Very good. Let's move on to learn more about types of forces.
Wow! They all seem to be applying a lot of force, but nothing is happening. How do you explain that?
So far, you have seen effects of single forces in terms of pulling and pushing. But in real life, there are often multiple forces acting on a body simultaneously. For example, in this case, there are an equal number of people on both sides. So, the force applied on one side of the rope is being counteracted by the force applied by the other side of the rope. That is, the force on both sides is balanced.
Does that mean there will be no movement if forces are balanced?
That's right. In such cases, because force is a vector, we must consider the result of the multiple forces acting on the body. This resultant force is called the net force. Net force is the sum of all the forces acting on the body. The magnitude and direction of the net force on the body depends on the magnitudes of the individual forces and their directions. If two forces, Fa and Fb, act in the same direction on a body, then the net force, Fa plus Fb, acts in that direction. In the same setup, if Fa acts in the direction opposite to Fb, and Fb is greater than Fa, then the net force becomes Fb minus Fa, and acts in the direction of force with the greater magnitude, that is, Fb. In case of multiple forces acting on a body, when the net force is zero, the forces are known as balanced forces. For example, this game of tug-of-war.
Doesn't look like this game is going to end. Neither of the teams seem to be making any progress.
Yes, this game will have to be a draw, unless we do something to tip the balance of the force. Let's see what happens if we add a person on one of the teams. See, the team with more people won. That's because adding another person made the forces on both sides unequal, and the net force was no longer zero. In such a case, the forces are said to be unbalanced. The concept of balanced and unbalanced forces applies to objects at rest as well as moving objects. When forces are balanced, a stationary object remains at rest and a moving object continues to move at the same speed and in the same direction. When forces are unbalanced, the object may change its state from rest to motion or vice versa, or change its speed or direction of motion in the direction of the net force. Let's observe this game of cricket. As you can see, the ball, when hit by the batsman, slows down and stops after rolling a certain distance. Do you see any force being applied to stop the ball?
No. Ideally, the ball shouldn't stop, right? No one applied any force to stop it.
The ball stopped due to a force called friction. Friction is the force resisting the relative motion of two bodies that acts along the surfaces it contacts. The bat hits the ball with a certain force that makes the ball move ahead. When the ball rolls down the field, friction acts in the direction opposite to the direction of the motion of the ball. Gradually, the frictional force overcomes the force that made the ball move, slowing down and eventually stopping the ball.
Is friction the same on all surfaces?
That's a good question. Look at this.
It needed a lot of force to push the block in the first case.
And yet, in both the cases, it is the same block.
So was it the type of surface that made the difference?
Yes. Rough surfaces offer more friction, while smooth surfaces offer minimal friction. That's why, when you try pushing a wooden block kept on a rough surface, you need to apply a relatively large amount of force to move it. Conversely, if you push the same block on a slab of ice, it moves relatively fast. You find friction at work almost everywhere around you. Some examples are objects lying on a slightly inclined plane. Pens, pencils, and chalk in use. Automotive brakes. And foes between vehicle tires and the road when in motion. This brings us to the end of this lesson on foes. In this lesson, you have learned about effects of foes, characteristics of foes, balanced and unbalanced forces, and friction. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.